On April 16, 2025, a team of astronomers led by Niku Madhusudan at the University of Cambridge held a press conference that briefly made an exoplanet 124 light-years away one of the most talked-about objects in the entire solar neighborhood. Using data from the James Webb Space Telescope, the team announced they had detected chemical signatures in the atmosphere of a planet called K2-18B that, on Earth, are produced only by living organisms. Headlines around the world ran with some version of the same sentence. Webb had found signs of alien life. Some outlets went even further, dropping the qualifiers entirely. That's not quite what happened. And the actual story, what Webb really measured, what the claim actually was, and what happened to it over the following year as other scientists checked the math, is a far better demonstration of how real science works than the original headline ever was. Let's start with the planet itself, because K2-18B earned its reputation as an exciting target well before this specific controversy. It orbits a red dwarf star roughly 124 light-years from Earth, and it's considerably larger than our own planet, about 8.5 times Earth's mass, with a radius large enough to place it in a category astronomers call a sub-Neptune. Bigger than Earth, but smaller than Neptune, a type of planet that doesn't exist anywhere in our own solar system. Back in 2023, using earlier Webb observations, Madhusudan's team had already detected methane and carbon dioxide in K2-18B's atmosphere and proposed that the planet might be what's sometimes called a Hycean world, a theoretical category of planet with a deep, global liquid water ocean sitting underneath a thick, hydrogen-rich atmosphere. That 2023 paper also noted a weak, uncertain hint of something else entirely, a possible trace of dimethyl sulfide, or DMS, a molecule that, on Earth, is produced almost exclusively by marine phytoplankton and bacteria. At the time, that hint wasn't considered strong enough to make any real claim about. It's worth understanding why the Hycean hypothesis generated so much genuine scientific interest in the first place, separate from anything to do with the later DMS controversy. K2-18B's measured mass and radius together produce a mean density that's genuinely ambiguous, consistent with several very different possible internal structures, according to independent modeling work. One possibility is a scorching magma ocean sitting underneath a thick hydrogen atmosphere. Another is a genuine liquid water ocean under a comparatively thin hydrogen envelope, the scenario Madhusudan's team favored. A third possibility is that the planet has no well-defined solid or liquid surface at all, and instead transitions gradually from atmosphere into a dense, supercritical fluid layer the deeper you go, with pressure and temperature increasing steadily rather than hitting any sharp boundary. Distinguishing between these genuinely different pictures of the same planet has required 6 separate transit observations using Webb so far, and the debate over which interior structure actually matches the data remains genuinely unresolved, even without factoring in the DMS question at all. The April 2025 announcement was built on new additional Webb observations, this time using a different instrument called MIRI, tuned to mid-infrared wavelengths. According to Madhusudan's team, this new data strengthened the earlier tentative DMS signal and also pointed to a related molecule called dimethyl disulfide, or DMDS. Both molecules matter specifically because, as far as anyone currently knows, there's no significant non-biological process that produces them in meaningful quantities. On Earth, at least. They're about as close to a direct chemical fingerprint of living organisms as atmospheric science currently has. On Earth specifically, DMS is produced overwhelmingly by marine phytoplankton and certain bacteria as part of their ordinary metabolic processes, released into seawater and eventually the atmosphere in large enough quantities that it's considered one of the dominant natural sources of atmospheric sulfur globally, playing a documented role in cloud formation over the open ocean. Here's where the story needs real precision, because the difference between what was actually claimed and what got reported afterward is enormous. Madhusudan's own published result described the detection at a confidence level of roughly 3 standard deviations, often written as 3 sigma. In statistics, sigma is a measure of how likely a given result is to have occurred purely by random chance, rather than reflecting something real. 3 sigma corresponds to roughly a 1 in far few hundred chance of being a random fluke, genuinely interesting and worth publishing, but nowhere near the standard astronomers and physicists typically require before calling something a confirmed discovery. That standard, by long-established convention across physics and astronomy, is 5 sigma, a threshold corresponding to roughly a 1 in a few million chance of a false positive. The difference between 3 sigma and 5 sigma isn't a small technical footnote. It's the entire difference between an intriguing signal worth investigating further and a confirmed result. To make that gap concrete with an example from outside astronomy entirely, the 5 sigma standard is the same threshold particle physicists required before officially confirming the discovery of the Higgs boson in 2012, After decades of searching and enormous amounts of collision data from the Large Hadron Collider, physicists didn't accept 3 sigma or 4 sigma hints along the way as confirmation, even when those weaker signals generated real excitement within the field at the time. They kept gathering data specifically because history has repeatedly shown that 3 sigma and even 4 sigma signals in physics and astronomy have a meaningful tendency to disappear entirely once more data comes in, revealed as statistical noise rather than genuine discoveries. That historical pattern is precisely why the field treats the 5 sigma threshold as a hard requirement rather than an arbitrary bureaucratic hurdle, and it's exactly the kind of caution that turned out to be justified in K2-18B's case as well. Madhusudan himself was notably careful about this distinction in his own public statements, even as media coverage raced past it. He described the result as the strongest evidence yet for a possible biosignature beyond the solar system, while explicitly cautioning that it fell short of the threshold needed to claim a confirmed detection of either the molecules themselves, or further still, of actual biological life. NASA's own response to the announcement, given directly to the Washington Post, was similarly careful. The agency stated that detecting a single potential biosignature would not, on its own, constitute a discovery of life, and that confirming true biosignatures would likely require multiple independent, converging lines of evidence, quite possibly for more than one mission entirely. That NASA statement is worth reading closely because it reveals something important about how the agency operating Webb itself viewed the announcement in real time, separate from how the researcher's own university handled the press rollout. Rather than issuing an enthusiastic endorsement alongside the Cambridge team's press conference, NASA's communications specifically distanced the agency from language describing the result as a discovery of life or as containing true biosignatures. Measured, careful phrasing that stands in fairly stark contrast to how much of the surrounding media coverage actually treated the story that same week. That gap between the announcing institution's own caution and the broader public narrative that followed is, in many ways, the central tension this entire story is built around. That caution turned out to be well justified, because the months following the announcement produced exactly the kind of independent scrutiny careful science is supposed to invite. Several separate research teams went back to the same raw Webb data Madhusudan's group had used, applying their own independent analysis methods, and the results were not kind to the original claim. A team led by Raphael Luque at the University of Chicago reanalyzed the same Webb readings, incorporating additional data from other telescopes, including Hubble. According to their published findings, the statistical evidence for either DMS or DMDS in the data simply wasn't there. The specific spectral features Madhusudan's team had attributed to those molecules could be explained just as well by other, far more mundane candidates, including ordinary hydrocarbons like ethane, molecules with no connection to biology whatsoever. The Luque team's paper was direct in its title, describing the evidence as insufficient for either molecule, based on a joint analysis combining data from 3 separate Webb instruments, NIRIS, NIRSPEC, and MIRI, rather than relying on any single instrument's readings in isolation, precisely to check whether the original signal held up consistently across all the available data, rather than appearing in just one narrow slice of it. A separate team led by Luis Wellbanks reached a closely related conclusion in the journal Nature Astronomy, using what's called an agnostic retrieval approach, a deliberately broader statistical method that doesn't start by assuming DMS is the correct explanation, but instead tests the full range of molecules that could plausibly account for the observed spectrum. According to Wellbanks and his colleagues, the current data simply doesn't robustly constrain the atmosphere toward any biosignature gas at all, and remains fully consistent with a range of non-biological molecules instead. The distinction between Madhusudan's original approach and Wellbanks' agnostic method is itself worth understanding. The original analysis effectively asked, how well does DMS explain this data? While the agnostic approach asked the more open-ended question, out of every plausible molecule, which one actually explains this data best? A meaningfully different and arguably more rigorous starting point that doesn't risk favoring a specific, exciting hypothesis simply because it was the one being tested first. A third independent analysis, published by researcher Jay Taylor, reached the same basic conclusion working from the same MIRI dataset. The disputed spectral features sit right at the edge of the instrument's noise threshold and aren't uniquely attributable to DMS or DMDS specifically, because several other sulfur or carbon-bearing molecules fit the same data comparably well. And when NASA's own follow-up study revisited the numbers directly, their reanalysis found a signal at roughly 2, 7 sigma confidence, if anything, slightly weaker than Madhusudan's original 3 sigma estimate, not stronger. That NASA-affiliated reanalysis is particularly notable, because it wasn't conducted by outside skeptics with any obvious motivation to undercut the original claim. It came from researchers working with the same broader institutional infrastructure that operates Webb itself applying careful, independent statistical methods to the same underlying data set and arriving at an even more cautious number than the original announcement had reported. It's worth pausing on why so many capable, well-resourced research teams could look at the same exact data set and come away with such different headline conclusions, because it's not simply a matter of some scientists being more careful than others. Extracting a molecule's specific signature from a planet's atmospheric spectrum is a genuinely difficult statistical problem, especially when the planet in question is small, distant, and only briefly passing in front of its star during each individual observation. Different research teams make different choices about how to process the raw instrument data, which background noise sources to model, which molecules to include as candidate explanations in the first place, and how to weigh weak, overlapping spectral features against each other. Those choices, each individually defensible, can meaningfully shift the final statistical result, which is exactly why a single team's initial analysis, however careful, isn't treated as the final word in a field where the underlying signal is this faint to begin with. There's a specific technical problem underlying much of this disagreement worth naming directly, a phenomenon researchers call spectral degeneracy. Methane, which is present in K2-18B's atmosphere in genuinely large quantities and detected with far higher confidence than DMS ever was, happens to absorb light at wavelengths that significantly overlap with where DMS itself would be expected to show up, particularly in the specific wavelength range covered by Webb's NIR spec instrument. Because methane's signal is so much stronger, separating out a comparatively faint DMS signature from the tail end of methane's much larger absorption feature becomes an inherently difficult statistical disentangling problem, one where reasonable researchers, using slightly different modeling assumptions, can genuinely arrive at different answers about how much of the observed absorption belongs to which molecule. This isn't a flaw unique to any single team's methodology. It's a fundamental limitation of the underlying data itself. At the current level of precision, Webb is capable of delivering for a planet this distant. The scientific community's reaction, beyond the formal published rebuttals, was similarly split and worth walking through honestly rather than pretending everyone agreed. Sarah Hurst, a planetary scientist at Johns Hopkins University, pushed back directly on social media, pointing specifically to laboratory experiments showing that DMS can be produced through entirely non-biological chemical pathways, undermining the assumption that its presence alone would prove anything about life. That point turns out to matter enormously for the underlying scientific argument, independent of any statistical confidence question. Even if DMS were confirmed on K2-18B with full 5 sigma certainty, that alone wouldn't automatically prove biology was responsible. Researchers have specifically documented DMS production through purely chemical, non-living processes, including in the atmosphere of comet 67P, studied directly by the European Space Agency's Rosetta mission, where DMS was detected without any plausible connection to life whatsoever. That single comparison point is a genuinely important piece of context largely missing from the original wave of coverage. DMS being biogenic on Earth doesn't mean DMS is exclusively biogenic everywhere, under every possible planetary condition. Ethan Siegel, an astrophysicist and science writer, published a piece bluntly titled "Describing the Evidence as Flimsy at Best." On the other side, astrophysicist Adam Frank of the University of Rochester expressed genuine excitement about the result publicly, reflecting real, honest disagreement among working scientists about how seriously to weigh a 3 sigma signal on a genuinely novel kind of measurement. That range of reactions was eventually captured more formally, too. A survey of astrobiologists, published in Nature Astronomy roughly a year after the original announcement, asked researchers directly whether they believed scientists had probably found evidence of extraterrestrial life on K2-18B. Only about 6% of respondents agreed. That's a genuinely useful, concrete data point to consider on its own merits. Entirely separate from any individual statistical reanalysis, it tells you how the people whose entire careers are built around exactly this kind of question actually assessed the claim, once the initial excitement had settled and the independent follow-up studies had time to circulate. That single number is worth sitting with for a moment because it's a genuinely rare thing to have. A direct, surveyed measurement of expert consensus on a specific, high-profile scientific claim, rather than just a scattered collection of individual quotes and opinions pulled from social media and press coverage. A field where the overwhelming majority of specialists, more than 93% of those surveyed, declined to say the evidence probably showed extraterrestrial life is a field that, by its own internal standards, has not accepted the original claim, regardless of how the initial headlines were phrased back in April 2025. That's not the same as the field concluding the claim was fraudulent or dismissible. Plenty of working astrobiologists likely view the underlying signal as a genuinely interesting open question still worth pursuing. But worth pursuing further, and probably already found, are 2 very different positions. and the survey data makes clear which one the field actually holds. So pulling this together, where does the claim actually stand as of right now, in the summer of 2026? The honest answer is that the evidence available today does not support saying Webb found life on K2-18B, and it doesn't even securely support saying Webb found DMS or DMDS there at all. Multiple independent teams, using different statistical methods and, in some cases, additional outside data, have failed to reproduce the original team's confidence in the detection, let alone its interpretation. That's not the same as saying the original team acted in bad faith, or that the story is over. Madhusudan's own published language was genuinely careful from the very start, explicitly framing the result as suggestive rather than confirmed. It was primarily the surrounding media coverage, not the underlying scientific paper, that collapsed an intriguing 3 sigma signal down into Webb-found alien life. And it's worth being honest about exactly where that gap opened up, rather than letting the original researchers take the blame for headlines they didn't write themselves. What actually happened here is, in a real sense, science working exactly as it's supposed to, even though it doesn't produce the same kind of tidy, satisfying story a single triumphant announcement would have. A genuinely interesting, previously unconfirmed signal showed up in real data. It got published, with appropriate caveats attached from the start. Other researchers, with no obligation to agree, went back and checked it using independent methods, additional data, and different statistical assumptions. Several of them found the original claim didn't hold up under that additional scrutiny. None of that makes the original observation worthless. It produced, by any honest account, one of the most detailed atmospheric spectra ever collected for a temperate sub-Neptune more than 100 light years away, and it forced the field to directly confront exactly how rigorous the evidence needs to be before anyone can responsibly claim a genuine biosignature. K2-18B remains a genuinely interesting, still only partially understood planet, still potentially hydrogen-rich, still possibly, though far from certainly, hosting some kind of ocean beneath its atmosphere. What it very likely isn't, based on where the evidence actually stands today, is a confirmed detection of alien life, or even a confirmed detection of the specific molecules that sparked the entire conversation in the first place. There's a broader lesson in this specific episode that extends well beyond K2-18B itself, and it's worth naming directly rather than leaving implicit. As Webb and future telescopes continue pushing toward genuinely Earth-like planets, this exact pattern, an exciting, borderline significant signal, followed by months or years of independent verification attempts, followed by either confirmation or retraction, is very likely to repeat itself again and again. Researchers in the field have specifically proposed formal frameworks, sometimes called standards of evidence for biosignature claims, explicitly designed to prevent a repeat of exactly the kind of premature public excitement that surrounded the original April 2025 announcement. The stated goal of that kind of framework isn't to discourage researchers from reporting genuinely interesting signals. It's to make sure the public conversation around those signals, including how they get reported by journalists and understood by everyone watching from home, stays honestly calibrated to the actual statistical confidence involved, rather than collapsing a 3 sigma hint into a 5 sigma discovery somewhere between the research paper and the headline. It's worth stepping back and asking what would actually need to happen for a claim like this to eventually clear the bar the field requires, because that's really the more interesting forward-looking question buried underneath all the back and forth. Reaching 5 sigma confidence on a signal this faint from a planet this far away likely requires substantially more observing time with Webb itself, ideally using multiple different instruments to cross-check any candidate signal against each other, the same way the original DMS claim was partially built by combining NIRSpec and MIRI observations in the first place. Beyond that, NASA's own stated position that confirming a genuine biosignature would likely require multiple independent converging lines of evidence, potentially from more than one mission entirely, points toward instruments not yet operating today. Future observatories currently in development, including missions specifically designed around direct imaging and detailed atmospheric characterization of smaller, more Earth-like planets, are widely viewed within the field as the kind of tool that could eventually settle a question like this with genuine confidence, rather than the frustratingly narrow 3 sigma signals that Webb, for all its genuine power, is currently working at the very edge of its capability to extract from a planet this distant. It's also worth examining, briefly, how the gap between 3 sigma signal and Webb-found alien life actually opened up in the first place, because understanding that gap is useful for reading the next big space headline too, not just this one. University press offices, competing for attention in an increasingly crowded media environment, have strong incentives to frame research results as dramatically as the underlying science can plausibly support, and sometimes push slightly past that line. Journalists working on tight deadlines, often without deep training in statistical significance, frequently compress careful, hedged scientific language into punchier, more shareable headlines. And audiences, understandably, respond far more strongly to scientists find alien life than to researchers report a 3 sigma spectral anomaly consistent with, among several other possibilities, a molecule associated with biological activity on Earth. Each individual step in that chain is a small, human, largely understandable simplification. Stacked together across a press release, dozens of news outlets, and millions of individual social media shares, those small simplifications compound into a genuinely misleading final picture, even when no single person along the way set out to mislead anyone. That compounding effect is precisely why direct primary sourcing matters so much for a story like this one, and why chasing down the actual published sigma value is worth the extra effort rather than accepting the headline version at face value. The original scientific claim, read carefully in Madhusudan's own words, was never, "we found aliens." It was closer to, "we found something interesting, worth taking seriously, that doesn't yet meet our own field's standard for confidence." A genuinely newsworthy statement in its own right, just a meaningfully different one than what ended up on most front pages that week in April 2025. There's also a specific technical detail about the 2023 versus 2025 observations worth including here, because it explains why the team returned to this exact question with new data in the first place, rather than treating the original 2023 hint as settled. The 2023 observations relied primarily on Webb's NIR-spec instrument, which operates across near-infrared wavelengths, and had already produced a weak, statistically inconclusive suggestion of DMS, well below any publishable threshold on its own. Rather than abandoning that early hint entirely, Madhusudan's team specifically requested additional observing time using MIRI, reasoning that mid-infrared wavelengths might capture a cleaner, less degenerate signal, separated further from methane's overlapping absorption features than the original near-infrared data had been. That's a genuinely reasonable scientific strategy, using a different instrument specifically chosen to sidestep a known technical limitation from the earlier attempt. It simply turned out, once independent teams checked the new MIRI data as carefully as the original NIR-spec data, that the underlying ambiguity hadn't been fully resolved after all, just shifted into a different, still genuinely contested statistical picture. Taken together, the K2-18B episode offers something genuinely valuable precisely because it didn't end in a clean confirmation. A real-time, fully public demonstration of the entire evidentiary process. Serious biosignature claims are now expected to survive, documented across dozens of peer-reviewed papers, formal statistical frameworks, and even a direct survey of expert opinion, all generated within about a year of the original announcement. Future claims about potential signs of life elsewhere in the galaxy will almost certainly follow a similar arc. An initial, exciting result, followed by months, sometimes years, of independent verification attempts. And having a clear, honest record of exactly how this particular claim was tested, and largely didn't hold up, gives everyone watching the next one a genuinely useful template for how to evaluate it. If you want to check any of this yourself instead of taking my word for it, everything in this video is drawn from Niku Madhusudan's original 2025 paper and public statements, the independent rebuttal papers published by Raphael Luque, Luis Wellbanks, and Jay Taylor, NASA's own follow-up reanalysis and public statements to the Washington Post, and the Nature Astronomy Astrobiologist Survey, along with reporting from Astronomy Magazine, Space Daily, and Ars Technica, covering the full arc of this story as it unfolded across 2025 and into 2026. Each of the independent rebuttal papers referenced here went through the same peer review process as the original claim itself, meaning they weren't casual social media pushback, but formal published scientific work subjected to the same scrutiny the original announcement received. I'll leave the specific sources referenced below so you can go verify the sourcing yourself. So, did James Webb just find life on K2-18B? Based on everything the actual published research says, as opposed to the headline from April 2025, the honest answer is no, not yet, and quite possibly not this specific signal at all. What Webb did find was a genuinely faint, genuinely interesting chemical hint, sitting right at the edge of what current instruments can reliably measure, that triggered exactly the kind of rigorous, occasionally messy, entirely public scientific argument that a claim this significant should have to survive before anyone gets to call it confirmed. That's a less satisfying ending than "we found aliens." It's also the honest one, and I'd rather leave you with that than a headline that fell apart the moment other scientists actually checked the math. If there's a single takeaway worth carrying forward from this entire episode, it's less about K2-18B specifically, and more about how to read the next headline like this one, because there will almost certainly be a next one. A single announcement, however exciting, however prestigious the university behind it, is never the end of the scientific process. It's the opening move in one. The number that actually matters is rarely in the headline. It's the sigma value buried a few paragraphs into the actual paper, and whether independent teams, with no stake in the original claim, are able to reproduce it using their own methods and their own data. Let me know in the comments whether you think Webb or its successors will eventually clear that 5 sigma bar on a planet like this. And if you want the next update the moment new K2-18B data comes in, subscribe, because we'll cover it with the same sourcing and the same honesty every time.